Have you ever put an ice cube in a heated skillet and watch it transform from ice to water, then to evaporate out of the pan and make steam? What you're seeing is that piece of matter changing in its state. Hey everyone, welcome to this video on the states of matter. There are three primary states that matter exists in: gas, liquid, and solid. However, in very extreme cases, matter can exist in other states, like plasma, more specifically, hot plasma. Gas. Within a gas, particles have large gaps of space, and there's no specific pattern to their arrangements. The particles move very quickly and freely. Since there's a lot of space between particles, gas is compressible. Gas can easily flow since particles dart past each other, and gas takes the shape and volume of the container that it's in, since the particles move freely. Liquid. Particles within a liquid are much closer together, but they also do not have a specific arranged pattern. These liquid particles move, but not quite like gas particles. They vibrate, slowly move about, and they can also move past each other. Because the particles can move, a liquid can fill the shape of the container it's in. However, it will not fill the whole space like gas, depending on the volume of water to volume of container ratio. Since there is not as much space between the particles, liquid is not easily compressible. Liquid can flow pretty effortlessly, which is due to the particles' ability to slide and move past each other. Solids. Now, particles within a solid are very, very close together with very little, if any, space between each other, and they are generally arranged in a specific pattern. Typically, solids do not move about, but they will vibrate in place. A solid has an already fixed volume and shape, since there is little to no major movements of the particles. A solid is also not easy to compress because of the lack of space between the particles already. Solids do not flow easily because of the lack of movement of the particles and their inability to move past each other. Now, plasma. I mentioned that this only happens in extreme cases. Plasma is extremely hot gas that is ionized. Plasma has significantly different characteristics than the other three states of matter, so it is thought of as the very distinct fourth state of matter. However, it is closest in similarity to that of a gas. Having an understanding of what's going on with the particles within matter is very important. They're not just simply tiny pieces of solid or liquid or gas, they are molecules and atoms. What is happening with those molecules and atoms, their physical characteristics, is what decides their state.
Hi, and welcome to this video on electric charge. In this video, we're going to look at what electric charge is and how it's measured. Electric charge is a fundamental property of matter. All physical things in the universe are made up of matter. All matter is made up of atoms, and atoms are made up of particles. These particles can be positively charged, negatively charged, or neutral. Protons are positively charged, electrons are negatively charged, and neutrons have no charge at all, making them neutral. One property of electric charge is that it is additive. This means that when multiple charges of the same kind are put together, they add up to one big charge, be it positive or negative. And if we have a mixture of positive and negative charges, we can find the net charge of the overall mixture. For example, if we have an object made up of 14 protons, which are positive, and 12 electrons, which are negative, then we end up with a net charge of positive 2. We simply add 1 for each proton and subtract 1 for each electron. If the resulting number is positive, we have a net positive charge. And if the resulting number is negative, we'll have a net negative charge. Note that neutral particles will make no difference in the net charge. It's also important to understand the interaction between charged particles. All electrically charged particles exert a force on all other electrically charged particles, aptly named the electric force. The electric force is described by the equation F equals K times Q1 times Q2 all over d squared, where k is Coulomb's constant. Q1 and Q2 are the two different charges exerting a force on each other, and d is the distance between the centers of the two charges. Note that the sign for each of the charges will impact whether the force between them is attractive or repulsive. Specifically, if the calculated force is negative, opposite signs on the charges, then the force is attractive. If the calculated force is positive, same signs on the charges, then the force is repulsive. Note that since distance is in the denominator of the equation, the closer the two charged objects are to each other, the stronger the force is between them. Another interesting property of electrically charged objects is the electric field surrounding them. We can think of the electric field as lines emanating from the surface of the charged object. For negatively charged objects, we draw the lines with arrows pointing inward to the object. And for positively charged objects, we draw the arrows pointing outward. The closer and denser the lines are, the stronger the field is in that spot. Theoretically, these lines go on forever, but get weaker the further away they are from the charge. For two like charges, electric field lines will avoid each other and the electric force will push the objects apart. For opposite charges, the electric field lines will actually connect the two charges, and the electric force will draw them closer together. Visually, this is demonstrated by lines that extend all the way from the positive charge to the negative charge, indicating an attraction. All charged particles or objects in an electric field will experience the electric force. The equation for electric field is E equals K times Q all over d squared, where K is Coulomb's constant, Q is the charge of the object whose electric field we're measuring, and d is the distance from the charged object whose electric field we're measuring to the spot where we want to determine E. The value of the electric field changes depending on where you are. This is similar to the electric force, and it can be pretty easy to mix up the two equations. So, it's important to remember that the electric force describes the interaction between two objects and therefore includes a Q1 and Q2, and the electric field describes the field of one object, so it only has one Q. Charge, of course, is not limited to point particles like this. We can have large objects with a net positive or negative charge as well. Charge that is built up on object is called static electricity. Objects handle the buildup of charge in a few different ways. The two main categories are conductors and insulators. Conductors have electrons with the ability to move freely on them and therefore have the ability to have a flow of electrical charge through them. Since the electrons can move, the charge will disperse as much as possible for the given shape of the conductor. So, when a conductor, piece of metal, has attracted extra electrons, it will have a net negative charge dispersed over its surface. An insulator, on the other hand, does not have the ability to have freely flowing electrons and cannot have a flow of electrical charge like a conductor. They can still build up a static charge, but it will be localized since it cannot disperse. Common examples of insulators are glass and wood. Now that we have an understanding of what electric charge is and how it causes electric forces and fields, let's think about some examples. Number 1. What is the net charge of an atom composed of 17 protons, 17 neutrons, and 18 electrons? Is it A, -1, B, +1, C, 0, or D, -18? The answer is A, -1. The neutrons have no effect on the charge, so -18 plus 17 equals -1. Number 2. Imagine a very large metal plate that has a net negative charge. In the middle of the plate, just above it, you place an ionized helium atom containing 2 protons, 2 neutrons, and 1 electron. What will happen to this atom? A, the atom will move directly upward away from the plate. B, the atom will move directly downward toward the plate. C, the atom will remain where it is. Or D, the atom will move to the right. The answer is B. Since there are more protons than electrons in the ionized helium atom, it has a net positive charge and would be attracted to the negatively charged plate and move downward.
You plug in your cell phone to charge. You hear the roar of a car engine as it starts. You turn on a flashlight when the power goes out. These are a few examples of electric circuits. They bring electricity from a power source to an item that converts that power into something else. These circuits are made up of a power source, wires, and other components like switches and resistors. Think about the plumbing in a house. The pipes deliver water to places where you use the water, like your sink and shower. Similarly, electric circuits deliver electricity to items and places that can use that electricity, like a light bulb, refrigerator, or TV. Circuits deliver electricity using the flow of electrons through wires, and this flow is called an electrical current. Just like the water pipes create a flow of water molecules making up the water current, the circuit creates a flow of electrons making up the electric current. Current is measured in amperes, which is a unit of measure that tells us how many electrons are flowing through a point in 1 second. In order to cause the electric current to flow, a voltage is applied to the circuit. A voltage difference causes the electrons to flow, just like a change in water pressure causes the water to flow. We can also think of voltage like the pulsing of your heart to push blood through your body. Your heart pushes on your blood to create blood flow, just like voltage pushes on electrons to create current. Voltage is measured in volts, a unit of measure that tells us how good our power source is at pushing an electron. Just like water pipes have ways for the water to flow to be slowed, electric circuits also have ways for electric current to be slowed. This is called resistance. Resistance is like the diameter of the water pipe. A larger diameter water pipe has less resistance than a small diameter water pipe. Every material has an electrical resistance, and it is measured in ohms. We use the Greek letter omega to represent an ohm. This unit of measure tells us how easy it is for our electric current to move through the material. The wires in an electrical circuit have resistance, R. It is determined by the length of the wire, L, the resistivity of the wire, ρ, and the diameter of the wire, d, through the equation R equals ρ times L divided by d. In most circuits, we want the wires delivering the current to have as small a resistance as possible so the current can flow easily. However, high resistance can be useful in some situations. An incandescent bulb has a twisted piece of wire in it. When you flip the switch to turn on the light, the voltage pushes the current through the wire, which has a very high resistance, so it is difficult for the current to move through. The wire begins to heat up. Eventually, the wire is so hot, light is created. Light bulbs show us one way electricity can be used to change one form of energy to another. We are changing electrical energy into light and heat energy. Voltage V, current I, and resistance R are related through Ohm's law. V equals I, R. From this relationship, we see that increasing resistance while keeping the current the same means the voltage must increase. It's like using your thumb to spray water from a hose. You have increased the resistance for the water to flow through the hose. So, more pressure is needed to keep the same water current flowing. Resistors can be linked together in a long chain. This is called a series circuit. Linking resistors in this way means each resistor receives the exact same current. However, the voltage drops across each resistor are dependent on its resistance, R. Suppose we have 3 resistors in a row, R1, R2, and R3. We would like to replace these 3 resistors with only one resistor that has the same resistance as the original series. This is called an equivalent resistance. Since the current is the same in each resistor, the relationship is additive. R1 plus R2 plus R3 equals are equivalent. It's like connecting two garden hoses together. The hoses are in series and it takes more water pressure to push the water through the hoses. Similarly, it takes more voltage to push the current through many resistors in series. An example of resistors in series is a string of old Christmas lights. The light bulbs form a series of resistors. Each bulb has a resistance. If one bulb burns out, the entire string of lights does not light up. This is because the current has been cut off. To make the lights work again, you need to find the broken bulb and replace it, which can take a while. Newer strings of lights don't have this problem because the resistors are in parallel. This means they each have the same voltage across them, but different currents. If one bulb burns out, the rest of the bulbs still work because they still have current. The equivalent resistance of resistors in parallel is 1 divided by R equivalent equals 1 divided by R1 plus 1 divided by R2 plus 1 divided by R3. This relationship follows from Ohm's law, which shows us how the current branches into different resistors. Let's wrap up with a review question. I want to string together 15 strings of Christmas lights. As I add more and more Christmas lights to my string, the lights get dimmer and dimmer. Why? A, I do not have enough Christmas spirit. B, adding more lights adds more resistance. Or C, adding more lights adds more voltage. The answer is B. The Christmas lights add more resistance through more bulbs and more electrical wire. The strings of lights lose more energy to the wire's resistance as it gets longer. Remember the definition of resistance? And the bulbs receive less voltage. Hi, and welcome to this video on friction. Friction is a type of resistance that one object encounters when moving over another object. In this video, we'll look at the friction model and some examples of different kinds of friction. First, let's familiarize ourselves with normal force. The normal force is the component exactly perpendicular to where the two surfaces touch. When you stand on the ground, the normal force points up to the sky because the two touching surfaces are the bottoms of your feet and the ground. When you push a box up a ramp, the normal force is perpendicular to the ramp. In the standard model of friction, we consider friction to be proportional to the normal force. Frictional force, F, equals mu times N. The proportionality constant, mu, changes depending on if the object is in motion or is standing still. We use the coefficient of static friction when the object is not in motion. Suppose we have a very heavy box we need to push across the ground. Push lightly and the box doesn't move. So we start pushing harder and harder until suddenly the box starts moving. In this example, the box doesn't move at first because static friction resists the change in motion. As we push harder, static friction increases. However, we reach a point where the box suddenly starts moving. At this point, our model switches to kinetic friction, which is a constant to describe the frictional forces. This is our standard model of friction. Static friction is directly proportional to the normal force, and it increases until the object begins to move. Kinetic friction is a constant, and it is less than or sometimes nearly equal to the maximum static friction. Friction eats up energy you would normally convert into useful energy. We see this in static friction. Instead of an object moving as soon as you apply force, friction eats up that energy and resists the change. Then, kinetic friction takes away energy as an object moves. If you slide across the floor, eventually you come to a stop because kinetic friction resists your motion and slows you down. There may be times when you want to minimize kinetic friction. If you want to slide further across the floor, you can buff the floor with wax to make the floor more slippery. Another option is to spray your feet with cooking oil to create a buffer between the floor and your feet. In this case, the cooking oil acts as a lubricant and decreases the coefficient of kinetic friction. Another way we can lower friction is by using ball bearings and grease in wheels. The ball bearings help the wheel rotate more smoothly, and the grease creates a more slippery surface for the balls to roll over. Sometimes we actually want to increase kinetic friction. Let's say you're developing a new kind of abrasive substance for sandpaper. The abrasive substance creates a high coefficient of friction between a test surface and the paper. We can even do an experiment to pick the most abrasive substance from a range of options. Using the same amount of paper and a block of a given mass for each, attach a spring scale to the block and pull until the block starts to move. The maximum read from the scale is correlated with static friction. Then you can pull the block at a constant velocity to measure the kinetic friction. Now, our model isn't perfect. We are assuming kinetic friction is always constant. For low speeds, this is mostly true, but once you start going very fast, kinetic friction becomes dependent on velocity. One such example is skydiving. You're flying extremely fast through the air, gaining speed from the moment you jump, but eventually your speed is constant. This is called terminal velocity, and it happens because kinetic friction is proportional to the square of the velocity. Now that we've covered the basics of what friction is, here's an interesting example to test your knowledge. Engineers who designed the Mars rover Curiosity were very worried about Mars's atmosphere as the rover was landing on Mars. Why? A. The rover was going so fast that the kinetic friction from the molecules in the atmosphere could heat up the rover and blow it up. B. The normal force doesn't exist on Mars, so friction is infinite. C. They weren't worried because the atmosphere doesn't affect the rover's landing. Or D. Gravity is less on Mars, so the atmosphere doesn't matter, and they were worried over nothing. The answer is A. While gravity on Mars is less compared to gravity on Earth, the atmosphere on Mars is still thick enough to cause a fast-moving object to convert energy to heat because of kinetic friction. Engineers designed a special nose cone to protect the rover from the extreme heat. They also used a very specially designed parachute to slow down the rover to decrease the energy loss due to kinetic friction. This was particularly tricky due to the thin atmosphere. The parachute needs enough atmosphere to help slow down, which is really hard to do when there isn't much of an atmosphere to start with.
Hi, and welcome to this video on levers. We're going to discuss what exactly levers are, the physics behind how they work, and what different types of levers exist. A lever is a type of simple machine. In fact, it's one of the simplest machines out there. In its simplest form, it consists of two parts, a rigid bar and a fulcrum, which acts as the pivot. Using a lever makes it easier to lift or move an object. That is, it makes it easier to do work on an object. The force that is exerted on an object with the lever is referred to as the force on the load, and the force you must physically apply to the lever is called the effort. The trick to easily lifting an object with a lever is the distance between the force applied and the object to which it is applied. When we use a lever, we are able to apply a small force over a longer distance in order to achieve a greater force on the object we're doing work on. So the lever enables us to exert a force that we may not be able to exert with our own strength. Conversely, we could apply a great force close to the fulcrum to lift an object a greater distance than we could reach. Remember, work is defined by a force multiplied by the distance over which the force is applied. By the laws of physics, energy is always conserved. So when we put some amount of work into a lever by pushing one end up or down, we are actually still getting that same amount of work out of the lever at the other end, assuming no energy is lost in friction. Then we can substitute in F times D for the input and output work. Fn is the force we apply to the lever when putting in effort. D1 is the distance over which we apply that force. F out is the force the lever applies to the load we're moving, and D2 is the distance over which the lever applies the force. The important concept here is that while the amount of work isn't changing, the force applied by us can be different from the force on the load as long as the distances are different. This leads to the concept of mechanical advantage, or MA, which is a ratio that describes how much the force you are putting into the lever is amplified. MA is greater than 1 is what we're looking for, meaning the lever is applying a greater force to the load than what was supplied by the effort to move the lever. Often the mechanical advantage of levers is described in terms of torque, or TOV, which is a measure of the force applied to a position relative to the pivot point. The equation for torque is similar to work, except that the distance is measured from the pivot point to the location where the force is applied. As such, the equations look very similar, and both relationships can be used to determine the mechanical advantage. So mechanical advantage can then be written as MA equals R1 over R2, which is just the ratio of the lever arms. For this lever, R1 is the distance from the pivot to the point that effort is applied, and R2 is the distance from the pivot to the load. Not all levers look exactly like the levers we've shown so far. There are actually 3 different classes of levers. They represent the 3 different arrangements of fulcrum, load, and effort on a rigid object. Class 1 levers are like the 2 we've already looked at. These levers are defined by having the pivot point between the effort point and the load. Examples of this type of lever would be a seesaw or a crowbar. It should be pointed out that the pivot can be anywhere along the line between the effort and the load, not just in the center. In a Class 2 configuration of levers, the load is in the center between the pivot and the effort point. Examples of Class 2 levers are wheelbarrows or bottle openers. In the case of a wheelbarrow, the work is done on the load in the barrow. The pivot is at the wheel, and the user applies a force or effort on the handles. Class 3 levers are devices where the effort or force is applied between the load and the pivot point. An example of this type of lever would be something like a broom. When you hold a broom, one of your hands is the fulcrum and the other is supplying the force. In the case where your top hand is the fulcrum, this is a Class 3 lever since the load is the bristle end and the hand supplying the force is between the fulcrum and the load. Levers are everywhere. You can actually find instances of each class of lever in the human body. Lever devices can get more complex by combining multiple levers like in scissors, nail clippers, or bolt cutters. These are referred to as compound levers. Now that we've discussed the types of levers and how they work, let's test your knowledge with a couple of questions. Number 1, you have a simple Class 1 lever with the pivot point 2 meters away from one end with a box sitting on it. If the other end is 3 meters away, what is the mechanical advantage you get by pushing down on that end? A, MA equals 0.67. B, MA equals 1.33. C, MA equals 1.50. Or D, MA equals 2.30. The correct answer is C. The mechanical advantage can be found by the ratio of A over B, which is the distance of pivot to effort over the distance of pivot to load. Here, mechanical advantage equals 3 over 2 equals 1.5. Number 2, what type of lever is in action when you bend your arm? A, Class 1, B, Class 2, C, Class 3, or D, compound? The correct answer is C. The elbow acts as a pivot. Your bicep applies the effort on the forearm, and the load is the lower half of your arm and anything in your hand. That's all for our video on the physics of levers. Thanks for watching and happy studying.